All right, college geometry. I have a little rundown of the week 4 assignment. Just going to explain some of the work, and hopefully it went well for you. But if it didn't, here's your chance to learn a little bit and correct some of those mistakes. Looking at the first one, we got the square root of 225. Now this one, if you know your list of squares well, you can jump right to knowing that the square root of this is 15. But I wanted to show you with the key that you can use a factor tree, even if you don't know this is a perfect square, to get it to your final answer there. So the number ends in 5. You know that 5 is going to be a factor. I started off breaking it into 5 and 45. 5 is prime, so there's no more factoring there. We go to 45. You can break it up into 5 times 9. We have 5 again, so we know we're done there. And then 9 can split into 3 and 3. So if we look at the end of our branches, we got a pair of 5s. 1 5 comes out of the radical. We got a pair of 3s. 1 3 comes out of the radical. Now when multiple terms come out, they all get multiplied together on the outside. So 5 times 3 is going to give us 15 there. Looking at 2, we got the square root of 175. This time, instead of going 5, I was thinking, okay, this is, we get to this number in increments of 25. So I split it up into 7 and 25. 7 is a prime number, so we can't factor anything else there. 25, we can split into 5 times 5. So we got a pair of 5s. 1 5 comes out. 7 does not have a match, so it's staying in. So remember, 5 has a date, it's going out. 7 does not have a date, so it's staying home in the radical. Looking at number 3, we got negative 2 on the outside. We got 289 on the inside. This one is actually another perfect square. Its factors are 1 and 289, and then 17 and 17. So this one, hopefully you guys are checking your square roots at the beginning. You could use a calculator if you want. Just realize right away, like, oh, okay, I don't need to do any extra work. I did factor tree it just in case. We got 17 and 17. They're both prime. We could circle those. So 17 comes out. Remember, we already have a negative 2 on the outside, so we're going to multiply those together, and we get negative 34. All right, looking at page 13. So we start off with, we have 7 radical 18. 18 we can break apart into 9 and 2. The 2 is good to go there. The 9 we can split into 3 and 3. So we already have that 7 on the outside. Because of the pair of 3s, we got a 3 coming out, and then 2 does not have a date. It's staying home. So we got 7 times 3 is 21, and then the radical 2 is going to be glued by multiplication, so they're just stuck together. Looking at the next one, we got 5 root 343. I just tried on my calculator. I tried 3 first. That didn't work. Tried a couple other numbers, worked my way up, and found that 7 was a factor. So we can break 343 into 7 and 49. 49 we can split into 7 and 7. So we already have 5 on the outside. This pair of 7s means 1 7 is coming out. The 7 that doesn't have a match is staying put in the radical. So 5 times 7 will give us 35, and then root 7. Looking at 6, we got an index card that's 3 inches by 5 inches. We're trying to find the length of the diagonal. So we're going to use the Pythagorean theorem. We got 3 squared plus 5 squared equals x squared. When we crunch that out, we got 9 plus 25 equals x squared. That adds up to 34. We got to take the square root of both sides. Now the square root of 34, this is where some common mistakes might happen. So we got factors of 2 and 17. So it does have factors, but notice how neither of those factors has a match. So when you don't have a match, those numbers will actually just stay put in the radical. Nothing comes out. You need a pair. So a common mistake would be to pull 2 or 17 or both, but neither one has a match, so they're staying in the radical, so they would get multiplied back together, or we just realize, okay, these factors came from 34, so it's going to be root 34 inches. All right, 7. We have our word problem inspired by the movie Holes, or the book Holes. Both of them are good. Anyways, we got Stanley Yelnats going 4 miles north, so we're going up, 2 miles east to the right, and then north and east are perpendicular, so we got a right angle there, and they want to know how long the journey would be if he just went straight to his destination. So again, we're going Pythagorean theorem. We got 4 squared plus 2 squared equals x squared. That's going to end up adding up to 16 plus 4 will give us 20, and then we take the square root of both sides. 20, we got factors of 2 and 10, and then 10 we can break apart into 2 and 5. So we got a pair of 2s, 1 2 comes out, 5's by itself with no match, staying put. So x equals 2 root 5 miles. Number 8, we got our classic ladder against a wall or house word problem. You'll see a lot of these. The ladder is 15 feet. It's 5 feet from the base or the bottom of the wall, so that's 5 there. We have a right angle there that I didn't fill in, so we do have that. And then we're trying to find the height of the wall. So this time x is not the hypotenuse, so it'll be on the left-hand side. So we got x squared plus 5 squared equals 15 squared. We crunch it out. We got x squared plus 25 equals 225. We subtract 25 from both sides. We got x squared equals 200. Then from there, we're going to take the square root of both sides because we want to figure out what x is worth. 200 we can break up into 100 and then 2. And then 100 is a perfect square, breaks up into 10 times 10. So pair of 10s, 10 comes out, 2's by itself, it stays put. So x equals 10 radical 2 feet, 10 root 2 feet. Looking at our last page where we're doing the converse of the Pythagorean theorem, we can classify a triangle by seeing how a squared plus b squared compares to c squared. So part A, we got 4, 4, and 5. So the biggest side always goes by itself when we check this. So we square everything out. 4 squared plus 4 squared, we get 16 plus 16, that's 32. Now looking at C, 5 squared is 25. So 32 is greater than 25, so that's going to be acute. Now the way that I remember these guys is the expressions less is more and more is less. If we look here, greater than, think more when you see that. So more is less, the smaller type of angle, acute. So we got an acute triangle there. Now, just to kind of get out ahead of it, none of these examples ended up being obtuse, but if you end up having a squared plus b squared being less than c squared, think less is more. Less than would mean that it's the bigger type of angle, obtuse. All right, looking at part B, we got 9, 10, and 12. 9 squared is 81, 10 squared 100, 12 squared 144. We're going to add 81 plus 100 to get 181. It is greater than 144, so we have an acute triangle there. Remember, more is less. Part C, we got 3 sides that are given to us as radicals. So we got root 9, root 11, and root 20. So the convenient thing here is when you square a radical, the radicand or the number inside just comes out. So root 9 times itself is just going to be 9. Root 11 squared is going to be 11. Root 20 squared is going to be 20. So right away we get into whole numbers there. So 9 plus 11 is going to be 20. 20 equals 20, so we have a right triangle there. So remember that with the converse of the Pythagorean theorem. If a squared plus b squared is greater than c squared, it's acute, more is less. If a squared plus b squared is less than c squared, it's going to be obtuse. So that's going to be less is more. And then if a squared plus b squared equals c squared, that's how right triangles always behave. So hopefully you guys, have that concept down by now. So again, a squared plus b squared is greater than c squared. More is less, we got acute. A squared plus b squared is less than c squared. Less is more, we get obtuse. And then finally, a squared plus b squared equals c squared, we got right. All right, so you guys know my email. Send me any questions you have.